Ladies and gentlemen, it's the time you've all been waiting for, the non-right triangle trigonometry unit. If you loved right triangle trig, you're going to love this just as much. And if you didn't like right triangle trigonometry, well, too bad. Learn to like it. All right, we got a situation brewing here with Justin Timberlake and Jimmy Fallon. They are standing 100 feet from each other, thinking about each other, and also thinking about how far they are from the lake at Camp Winnipesaukee. Now, as Justin looks at the dock of the lake and then looks at Jimmy, he has to turn 77 degrees. And when Jimmy looks at the dock at the lake and then looks at Justin, he has to turn 71 degrees. How far are each of them from the lake, or from the dock that is at that lake? Well, what's lovely here, guys, is we can, kind of map this out with some an imaginary triangle. So here's my lake, right? We'll call this the lake. Okay, and I've got a dock that that goes out into the lake. Now let's say we've got Justin is standing over here, and we'll say that Jimmy is over here. Now we said when, let's see here, as Justin looks at the dock at the lake, then looks at Jimmy, he has to turn 77 degrees. So the angle we're talking about, let me try that again, is this angle right here, 77 degrees. And then when Jimmy looks at the dock, then turns, this angle right here was 71. And we know that they are 100 feet from each other. And we want to know how far are each of them from that dock at that lake, right? Well, we'll call Justin's value X and we'll call Jimmy's value Y. Now, normally I think we just do some right triangle trig. If we've got a degree measure and a length, boom, we're good to go. But we can't do that here because this isn't a right triangle. We don't have a 90-degree angle. We also can't Pythagorean theorem this bad boy because it's not a right triangle. Everything we've dealt with thus far has been a right triangle, but not all situations are quite that easy. We don't always have right triangles in the real world. So now we're going to learn how to deal with it, all right? So there's this fancy formula called the law of sines, hence the title of this video here. It's called Unit 3, Day 6, Law of Sines. Now our law of sines is this. All right, so basically what we have here is this, we'll call it a super proportion, where you have a bunch of sine functions, sine of A, sine of B, sine of C, sine of all the angles, and then the sides across from them. So pending the information we have, we could use law of sines to find some missing values, okay? If I've got this angle and this side, I can set up a ratio of those two, and then if I have any other angle or side, I can solve for missing pieces, okay? So what we're going to do is we are going to apply this into our problem that we were just looking at a moment ago. All right, so my law of sines is basically just a bunch of ratios put together into a super proportion, if you will. I'm going to go ahead and figure out what this last angle is that's over by the dock. Any way that we could figure that out? Well, how many degrees are there in a triangle? If you said 180, that is correct. So if I take both 77 and 71, add them together, and subtract that from 180, I'm going to get 32 degrees up here, okay? So that angle right there is 32. That could be used here in this law of sines setup that we're going to be doing. All right. So I want to figure out what x is, right? So I'm just going to go ahead and put together this super proportion. We'll say this is my x, this is my y, and this is my 100. I've got all the sides down there, right? Now all I'm going to do is above them, I will put the sine of the angle that is across from it. So the angle that's across from the x is the sine of 71. And the angle that's across from the y is the 77, so it's sine of 77. And the angle across from the 100 is the sine of 32. It's the 32 is the angle, so I'll put sine of 32 up here. So the one that we're going to use the most is actually this guy over here, the one that involves both numbers, right? We got sine of 32, the sine of an angle, over 100. The other two have unknowns, the x and the y that we're trying to figure out. But we'll use that one that I boxed in red to figure out the others, okay? So what I'm going to do is I'm going to try and shrink some of this down over here so we got some room to work. Okay, so my sine of 32 over 100, and I'm going to solve for x first. So I'm just going to put sine of 71 over x. Now what I can do is I can cross multiply these two. So I'll have x times sine of 32 and 100 times sine of 71. Okay, so 100 times sine of 71 is equal to x times sine of 32. Now if I type in 100 times the sine of 71, I end up with 94.55. Cool. But how do I solve for x? Well, I need to divide by sine of 32 to get x alone. So I'm going to do that. I'm going to take that, divide it by the sine of 32, and I end up getting x equals approximately 178.4 feet. So this right here is how far Justin is from the dock. Cool. That sounds lovely. Now, before we go ahead and figure out how far Jimmy is from the dock, do we have any predictions as to whether or not he may be further or closer? Well, if we take a look at the angle here, I wonder if that would tell us anything. And also looking at this angle. Well, the angle by Jimmy is smaller, so maybe he's closer. But the angle across is bigger. I wonder if that has anything to do with it. Why don't we do the math, and then we'll make some conclusions from there. So let's figure it out for Jimmy now. We have the sine, we're going to use this one again, sine of 32. I'm going to move that up a little bit. Equals, and then when we're solving for y, it's the sine of 77 over y. So if I cross multiply, I'm going to run into basically the same type of problem. It's going to be 100 times sine of 77 equals y times sine of 32. So I will get y equals, let's type that in. So when I do 100 times sine of 77, I get 97.4-ish. I'm going to divide that by sine of 32, kind of like we did before. Again, just cross multiplying, but with trig functions, so extra fun. And when I plug that all in, I get 183.87, so 0.9 feet. All right. So that's how far Jimmy is. That length is a bit longer than how far Justin is from there. And I wonder why. Well, think about this for a sec. If I'm looking at this triangle, and this is a little beyond like what we're actually learning the new stuff here with the law of sines action that we got going on here, right? Our superproportion that we set up. This is more thinking about why we're getting a number that's larger for this one as compared to this one. Let's try and make sense of that. Well, if my angle over here is 77 compared to 71, 77 is bigger, right? So that means that this triangle is opening up a little bit larger, which would then cause for a larger opposite side. If you look at each one of these, across from the 32, our smallest angle is our smallest side. Across from the 71 was the 178.4, which was our mid-sized side, our mid-sized angle. And then our largest angle had the largest side across from it. Man, that is pretty cool. And that's just a theorem in our geometry class that talks about the relative size of sides compared to their opposite angle, right? Smallest angle across from it's going to be the smallest side. Largest angle across from it's going to be the largest side. That's pretty cool. That's pretty wonderful. But again, the new stuff is what we have right here with our law of sines. We're going to try one more example here, and then we will be moving on to law of cosines. Woo! All right, we got a couple more buddies here. We got Will Ferrell and John C. Riley that are building a bridge from their bedroom, the one with the bunk beds that allow room for activities, and stepbrothers. And Will stands where they plan to start the bridge, and he gets John to climb out onto the roof and stand 25 feet away from him. They have a tape measure, which is conveniently 25 feet long. So what they basically do is they form an imaginary triangle that you can't really see, but they're going to draw it out because they like mathing it out. They do it with each other as well as the treehouse. Those are the three vertices of the triangle. Now the angle by Will is 75 degrees, the angle by John is 68, and they figure this out with a fancy transit. Many other tools can do that as well, but they're using a transit, which you guys have been trained in. How long does the bridge need to be? Okay, well, why don't we start drawing a picture here? All right, so we've got ourselves Will and John here. They are ready to math it up so we can move them around. So we'll say Will is, he's in the bedroom, right, where they plan to start the bridge. And John is out on the roof, right? And we said that they are 25 feet apart. 25. Cool. Now the tree is somewhere out here. The angle from Will to the treehouse was 75 degrees, and from John to the treehouse was 68 degrees, right? So that's all the information I have right now. But let's look at the question here. It says, how long does the bridge need to be? Well, the bridge is going from Will, he stands where they plan to start the bridge, to that treehouse. So this is what I'm looking for. That's my x value that I want to solve for, right? That's the missing side of my triangle. I could figure out the other side as well, but do I need it? I'm not asked for it, so I'm not going to worry about it. Okay, so this is what I've got so far. Cool. Well, how do I figure this out? It's not a right triangle. Maybe I will use my fancy law of sines once again. So let's see what information I have when I set up my superproportion. So I've got, I'm missing an angle here. This angle right here could be pretty helpful because I know what the opposite side is, right? So if this is 25, I want to take the sine of its angle that's across from it. Well, how would I figure that out? How about, how many degrees are in a triangle again? 180 degrees in a triangle? Well, if I take 75 and 68, add them up and subtract them from 180, I'm going to get 37. Cool. So I'm taking the sine of 37 over the 25 feet. Now, I want to figure out this x right here, right? So let's put that x as my length down here. Well, what angle is across from it? Across from my x is the 68 degree angle. So my sine of 68 goes right up here. Sine of 68 degrees. Now, do I even care about this last piece over here? I do not. I do not care about that last piece for this particular problem, not solving for that length. All right, so I can just go ahead and cross multiply and solve here. So x times sine of 37, x times sine of 37 equals 25 times the sine of 68. And my last thing to do is sine of 37, dividing by that on both sides. So this goes away, I'm just left with x equals, well now it's calculator city. Let's type this bad boy in. So I've got 25 times the sine of 68. That's about 23.2, roughly, 23.1795, so on and so forth. And I'm going to divide that by the sine of 37. I end up getting 38.516, so 38.5 feet. The rough length of the bridge that they're going to build from the bedroom to the treehouse is about 38.5 feet long. And they did that without using right triangle trigonometry, just a tape measure and a transit. Man, that sounds awesome.